Welcome to the session 4 of our series of building the Streamlit dashboard with Python for stock prediction. Last session we completed prepare sequence data method and we created placeholder for train RNN and train LSTM, which create model of function we wrote in previous lessons. We are still at train and predict part of our code, and let's talk a couple of seconds for what this method's purpose is. The role of this method is to prepare and normalize sequential data, train a symbol-specific RNN model, apply regularization and training safeguards, and persisting both the model and the normalizing parameters of this. We will start with method signature. It will include symbol as a string and also prices, that would be MP and D array. And as a return, optional return, we're going to have a list of TensorFlow Keras model. Our line of execution of this method, train RNN model with improvement training, and we will wrap it into try and accept as usual, want to handle things gracefully. Now we are going to prepare sequence data with normalization. You remember for both RNN and LSTM, when we were creating, we had a duration of the data agreed to discuss later on, and for prepare sequence data we took interval of 60 days. So now is the time to merge those two together. Our look back be equal to 60. This will be the days that we are going to use in our training purposes. And next we are going to prepare X, Y, data mean and data standard deviation as self prepare sequence of the data, prices, and look back. Now, why this exists and what we are doing with it. This line here, this will convert raw prices into supervised sequences. This will normalize the data for stable gradient behavior, and this will return a normalization start for later denormalization. You remember that here we have return for prepare sequence data for NP-array and NP-array X, NP-array Y, data mean and data standard. Our key choice here is that the normalization happens before training, not inside the model. Now, we have 60 days data, but we want to establish the minimum threshold, like the minimum data based on which this analysis will happen. If length of X is less than 20, this has increased minimum data requirement. We are throwing here a logger warning, not enough data for RNN model for symbol, minimum required 20 days, and we will return none. So we will completely skip the part when our minimum data amount request is not met. What this will do? This will prevent training on tiny datasets. This will help for RNN overfit extremely fast and protects against unstable weights, meaningless models, and runtime errors downstream. Next, what we are going to do, we're going to reshape for RNN. X equals X, reshape, X shape 0 to X shape 1. Why we did this? Because RNN here expects the samples, the timestamps, and features. Feature count will be 1 as price only, and we are explicitly reshaping to prevent silent shape mismatches. Next, we'll create and train model. Model equals self, create RNN model, but as we already did the reshaping, so here we will just provide look back and 1. Now about this, why do we do this? We are separating the architectural definition from training logic. We are enabling reuse and experimentation and keep the method focused on orchestration. And when the model is created, next we are going to add early stop and reduce learning rate. Early stopping equals TensorFlow keras callbacks early stopping with monitor equal value loss and patience equals 5. Restore best weights equals true. Let's stop here for a second as well and understand what we created. We here are trying to stop training when validation loss stops improving. This will prevent overfitting and restore the best performing weights automatically. So we are introducing here bundle of Like, imagine you are on a train goes fast, but it goes on the wrong direction. So you need some kind of manual brake or something to push it, or just pull the plug on whole training stuff, because that's not what you want to do. You are simply putting uh, artificial bottlenecks on the training to avoid RNN training capabilities wasted on something unnecessary. Reduce learning rate equals TF keras callbacks. Reduce our uh, learning rate on plateau. And the argument here will be basically the same. Monitor equals value loss, and the vector is 0.5, patience is 3, and minimum learning rate equals to 6. And couple about this learning rate reduction. If the learning goes on plateau, which means that it's not increasing, so it's going strictly like in parallel with the axis x, so no learning improvement noticed. We are reducing the step size and allow fine-graded convergence. This is specifically important for the RNN stability. I know that it's not too much popular topic, because all of us wants to see, when predicting something, some shiny graphs, some beautiful numbers, but this is the hard way that we are going to go to ensure our models are uh, as good as we could create them for initial start, and then later on to go and make some improvements on it. Next, we are doing model fit x train, y train, validation, data, equals x validation, epochs equals to 50, and batch size equals 16, verbose equals 0, callbacks early, stopping, and reduce learning rate. But we forgot one item to proceed before this, so let's add it here. Splitting data for validation, split idx will be integer for length x or 8, x train value is x split I dx, and x the same for y train and y value equals to y split x. Now we good. Let's go over these few lines. We are doing train validation split multiplying by 0.8, time order split. This is time order split and not random. It prevents future data leakage and mimics real forecasting conditions. For the model fit, we are including into model fit the values that we just assigned for splitting and adding a number of epochs which allow learning temporal patterns and minimizing the batch size. With the smaller one, we will have more frequent weight updates and better generalization on noisy data. And we are including our called callbacks, which we called a couple of lines above. So let's continue. Now with model fit created and data splitted, we need to save the model. Okay. Here and add a comment, save model and normalization parameters, model path OS path join self models directory RNN F symbol RNN job loop. Oh, not job lib, it will be normal JSON. And normalization parameters be mean, which will be data mean, standard deviation, which will be float of data standard deviation. Why we are doing this? Because sometimes the data mean because this expects to be strictly converted to float, because value type can be different from the float. And now with open norm path in writing mode JSON dump norm params because we are doing a normalization part yet. Let's talk about these few lines too. For model persistence, what do? We excuse me. We are saving normalization parameters which are critical for correctness. The mean for data mean, and the STD for data standard deviation. Without this, our predictions would be in normalized space, and interference would produce meaningless values. So we have to avoid that too. Uh, Here we are just providing a path where to save our models, and after that we are just opening the path, opening the file in the provided path in RNN folder in models directory, and just uh, throw content into the JSON file. And after all of this, at the end, R will return model and our try and accept what we were trying to catch if any exception will happen. Exception as E, log your error training RNN model for symbol, and stringified error message. So once again, what we did during this lesson. We created a training model for our neural network, recurrent neural networks, which is preparing normalized sequential data. Here it is. Then it trains a symbol-specific model. It applies regularization and training safeguards in case anything goes wrong, for not having the good values or some other things that can have an influence of our model, and then persisting the model and its normalization parameters here. As a result, we are saving the train model content into specific file per symbol in RNN folder of our models directory here. And all this is wrapped into try and accept to handle exceptions or errors gracefully. This was all for today. At the next session we are going to work on LSTM model. It will be basically pretty close to what we did today, because most of the time those models act very similar to each other. Thank you for your time and see you at the next session. Bye bye.